Good morning, everyone, or good evening, depending where you are, and welcome to this webinar. Today, we are going to talk about protection systems and focus on IEC 61850 and traveling wave fault locators. We have four speakers. Myself, Romain Guilbault, Communication Protocol Specialist. I will talk about IEC 61850 data integrity manipulation. Shijali, Protection and Smart Grid Specialist, will talk about an FPGA-based HIL testing solution for traveling wave fault locators. Our special guest today is Ricardo Cartacho, Protect Researcher at R&D Nester, who will talk about HIL protection, automation, and control system testing. Finally, Etienne Leduc, Product Owner of Hypersim, will talk about the latest protection system solutions. Moving on with the first presentation. What exactly is the goal when you test IEDs and protocol implementation? What do you need to test? One could test the merging units, relays, PMUs, and other IEDs, all these independently from one another. One could also test how different IEDs from different vendors work together. Finally, one should test the complete system, from measuring the information down to sending it on a wide area network to a control center. Now, why should engineers test these features? One obvious reason is that the protocol may not be implemented according to the standard. Another less obvious reason is that the IED may not match the protection philosophy, and I'll get back to this point during my presentation. Finally, if every vendor does it, I quote, right and according to the standard, then why do multi-vendor implementations have failed in the past and continue to fail in some cases today? The reason is that there is a lack of good tools needed to have a deeper understanding of how IEDs work together. These are some of the hot topics that are discussed at the IOP every 2 years, the biggest meeting on the subject, where we saw last year that a number of cases that would still fail without apparent reasons. Now let me give you an example of what I call deep testing an IED. For this, I will take a relay subscribing to some sampled value streams. First, the standard specifies that IEDs, in this case relays, should operate smoothly when a delay happens on the network. To test this, we would create a normal stream. We would then make a delay on the stream. And after a certain time, the stream would be sent again, but with a delay of 5 milliseconds. In this example, and we could observe how the relay reacts. Now, what happens now if the packets are completely lost? Let's create a normal stream again, drop 1, 2, 3 or more packets, and see how the relay reacts. Then other questions appears about synchronization and quality bits and all the data contained in the packets. What happens when you do modifications in the sample value packets? We went ahead and tested these manipulations on 3 relays available on the market. We will call them A, B, and C. These relays are set as differential protection. The real-time simulator is sending 2 streams for the differential, which are sent to the relays. A power system fault will be triggered on one side of the protection so that the relays are in trip mode. This trip mode will be the base for data integrity manipulation tests because it's easier to see their effect. Let's start with a rather dramatic scenario to show what happens when 20 packets are lost during transmission. The simulator is sending the streams to the 3 relays. A power system fault is triggered, and then we apply a loss of packet on one of the streams. You can see the missing packets here. We can observe that the 3 relays have a different behavior as a result of this data loss. There is no good or bad result there. We are just showing that they behave differently. Note, though, that the relay C reset its trip signal for 275 milliseconds. A very similar test, but with more realistic scenario of 2 packets lost. There are the streams with the power system fault. We make 2 packets disappear from one of the stream and observe the results, which are very interesting. Indeed, if 2 packets are dropped by the network, only one relay keeps its trip signal activated. Note that the relay C now reset its trip signal for 610 milliseconds following a 2 packet drop. It is more than twice the time compared to the previous test, where 20 packets were dropped. It means that the number of packets that are lost doesn't have a direct influence on its behavior. The algorithm behind this action might be questionable. For the next test, let's try another dramatic scenario where a delay of 20 milliseconds would be applied between 2 streams. Here are the streams, the power system fault. Now, instead of sending all the packets directly on the network, one of the streams will be buffered for 20 milliseconds to create a delay. Here you can see when the delay is applied and then cleared. What happens is that the content of the buffer is released on the network all at once. You can see there the delay applied and then the buffer that is releasing its content on the network. It is clear that some relays take more time than others to recover from this event. Now that you get the test sequence, let's go a bit faster. If we retry this test with a more realistic delay, 1 millisecond for example, we can see that one relay reset its trip signal. It is interesting to see that a rather small delay of 1 millisecond has an impact on your protection scheme. Maybe your protection philosophy is not to act on delays, maybe it is. At the end of the day, the relay you choose should be based on this kind of results. Let's move on some other interesting tests. Here we have packet duplication, where we send all the packets 2 times. You can see that there is another difference between the relays. It is interesting to see that a bad network topology that is a likely mistake in a lab, but also in the field, has an impact on your protection scheme. On the synchronization topic now, let's see what happens when the synchronization bit, the SMP sync, goes from global 2 to known 0, which would indicate a loss of synchronization. Interesting result, again, the relay A doesn't really mind about the streams not being synchronized, while relay B and C stop their protection function. A last example with the quality bits, probably the most obvious data to test depending on your philosophy choices. Indeed, when the source quality bit goes from good to bad, we can observe that only relay C acts on it. This is, again, something to take into consideration when choosing a vendor, since maybe your philosophy is to take action on a bad source. Maybe it's not. Of course, many combinations can be tested with the different quality bits. Here is a quick look at the interface of the tool we used during this test. There are many options to choose from in order to create the exact manipulation scenario that you want to replicate. This is an overview where you can see the quality bits grid. It is possible to switch any bit for any length of time. You have the complete control over what happens in this case. You will find more information about IEC 62850 and data integrity manipulation on our website. Of course, these features are available for 62850 Lite Edition, Edition 2, 2.1, and 61869-9.